Hello, my name is Kason Kelly, and this is Lab 2, where we will study the properties of constant velocity and its relationship with position versus time graphs. Constant velocity is defined as motion in which an object covers equal distances in equal intervals of time without any change in speed. On a position versus time graph, constant velocity is represented by a straight line. The slope of that line represents the velocity. A steeper slope means the object is moving faster, while the direction of the slope, whether positive or negative, indicates the direction of motion. This makes a slope a very powerful tool for understanding motion. A practical example of this can be seen when a train is traveling at a steady pace along a straight section of track. If the train maintains the same speed without slowing down or speeding up, its position changes at a constant rate over time. On a graph, this would appear as a straight line with a constant slope, showing both the steady motion and the direction of travel. In this lab, we explored constant velocity motion using an air pump glider on a nearly frictionless track. The glider allowed us to closely model the type of motion shown on the given position versus time graphs. Our experiment focused on the glider's movement starting from its initial release and continuing until just before the second turning point. To study this motion, we used the multi-coordinate tool in Capstone to select three key positions: the initial position, the turning point where the glider changes direction, and the final position. We then recorded these values in a data table and used them to calculate velocity. The velocity was determined using the basic formula: V equals delta x divided by delta t, where delta x represents the change in position and delta t the change in time. Since velocity includes both magnitude and direction, the sign of the velocity value allowed us to identify which way the glider was moving along the track. After completing the calculations, we sketched a prediction of what the velocity versus time graph should look like. This step was important because it required us to apply our understanding of the relationship between position and velocity. Once the prediction was made, we used Capstone to generate the actual velocity graph for the glider's motion. We then compared the experimental results with our prediction and identified differences between the two. This process allowed us to connect the theoretical ideas of constant velocity with real data. By analyzing both our predicted graph and the one created by Capstone, we gained a clearer understanding of how velocity is represented in graphs and how direction plays an essential role in one-dimensional motion.
Hello, my name is Conrad and I will be doing the materials. The materials that we were using in this lab are as follows. We have the air track, we have the air pump with the blower, the glider with the flag for sensor detection, the motion sensor connected to Capstone software, the computer with Capstone software installed, and the power supply and connecting cables. This will be the first time we will be using the air track, the air pump, and the glider. The motion sensor, computer, Capstone, and connecting cables were used in the previous lab.
Hello, my name is Conrad and I'll be going over the procedure of the lab. In the first step, we have the equipment. So we placed the air track on a flat surface and connected it to the air pump. We turned on the pump and placed the glider at the center of the track. For Capstone, we connected the motion sensor to the computer and opened the Capstone software, select the position versus time graph, and verified that the sensor can detect the glider along the full length of the track. We data collection gently pushed the glider so that it can travels away from. We placed the glider at the starting position, and so that way it'll reach the endpoint and then return back to the sensor. The data recording. So for the graph itself, we did annotate the graph. We used the multi-coordinate tool in Capstone to mark and record the initial, turning point, and final positions. Our TA actually specifically told us, since we were doing graph 3, that since we had two turning points, TA said to replace the final turning point with the final position. So we only had the initial position, the turning point, and the final. So originally we would have initial point, and then it would go up away from the origin to the turning point, and then it would go down back to the origin to the turning point again, and then to the final position, which is another going away from the origin. But our TA instead told us to use the initial position, the turning point, and then the final position is the bottom when it hits the origin. We use the velocity formula, final minus initial position over final minus initial time. In Capstone, we also created a new velocity versus time graph to measure the velocity of the first graph. In the data comparison, we calculated the percent difference between the manually calculated velocities with the mean velocities given by Capstone using the percent difference formula.
Hello, my name is Gregorio Olivas, and I will be going over the data analysis. The first step was to create the table and to record the data we collected to calculate the velocity of the glide. For the initial position A, we recorded 15.55 seconds for time and 0 meters for the position. For the change direction, which was B, we recorded 18.9 seconds for the time and 1.22 meters for the position. Then lastly, for the final position of C, we got 20.85 seconds for the time and 0 meters for the position. The next step was to make another graph to find out the line between point A to point B, and another line from point B to point C. With these lines, we needed to calculate the velocity in meters per second. The equation for velocity is final position minus initial position over final time minus initial time, which once we calculated it, we got a mean velocity of 0.36 for the line of A to B and a negative 0.63 for the line of B to C. Now here is where we use Capstone to create the velocity versus time graph and the position versus time graph. Then we labeled everything according to step 4. Lastly, we calculated the difference percentage based off of the mean velocity and the hand computed velocity. From line A to B, we got 0.36 meters per second mean velocity and 0.08 meters per second hand computed velocity, which gave us a total difference of 127%. Now from line B to C, the mean velocity was negative 0.63 meters per second and the hand computed velocity was negative 0.26 meters per second, which gave us an 83% difference.
In summary, Lab 2 provided us with the opportunity to explore the characteristics of constant velocity and its representation through position versus time and velocity versus time graphs. By utilizing our air pump glider on a nearly frictionless track, we successfully recreated a motion pattern and examined it closely. We concentrated on 3 significant aspects of the glider's movement: the starting position, the turning point where the direction shifted, and the ending position. Documenting these values in a data table laid the groundwork for calculating velocity using the equation v equals delta x divided by delta t. This process showed that velocity is defined not just by its magnitude, but also by its direction, which in one-dimensional motion is indicated by the sign of the value. After determining the velocity, we anticipated the shape of the velocity versus time graph and subsequently created the actual graph using Capstone. The comparison between our predictions and the experimental outcomes revealed that while the general trends were aligned, there were slight variations. These variations could be linked to experimental factors such as minor friction or timing errors. Acknowledging these discrepancies was crucial as it underscored how theoretical motion and actual data may not always perfectly coincide. In conclusion, this lab reinforced the connection between position, velocity, and time, while also illustrating the significance of precise measurement and analysis in experimental physics. That wraps up Lab 2, and thank you for tuning in.
Hello, my name is Gregorio Olivas, and I will be going over the credits. So, Conrad did the materials and the procedure, Kaysen did the introduction and the conclusion, and I did the data analysis, the credentials, and all of the editing of this video. Thank you.
Hello, my name is Conrad, and we are Group 6 now. We were originally Group 3, but we switched over to Group 6 after the groups were moved over. Now we are with Santiago Arras, Stephanie Howard, and Jorge Valdez. For our video, we decided to use Argu's video because Argu's video was more clean, and therefore we've decided to upload this video instead of the other video.